In my previous video I calculated the dip correction to the horizon using this formula. Dip angle equals 1.932 times the square root of the observer height, where the dip correction is in arc seconds. I calculated the distance to the horizon, assuming a flat earth. And assuming that Nathan Oakley was right when he claimed that the dip correction was for the distance of the observer to the flat plane only. My calculations showed that with this way of thinking, and I use that word lightly, the horizon was much closer by than when calculated on a spherical Earth, using quantum eraser's formula stating that the distance to the horizon in miles equals 1.22 times the square root of the height of the observer in feet, which killed the whole black swan argument altogether. Not that it was necessary, it was dead for some time already. I also showed a table from a nautical almanac where you can see the different dip corrections in relation to different observer heights. When I took a second look at the overview of the dip corrections for celestial navigation with the sextant, I noticed that there was an extra column with the distance to the horizon. So I decided to calculate the distances to the horizon for 18 different observer heights, both for a flat Earth and for a spherical Earth. The calculated distance to the horizon on a flat Earth came out to be slightly more than half of the given distance, with an average deviation of 87.42%. I noticed that the given distances to the horizon were greater than would be calculated with the formula distance in nautical miles equals 1.17 times the square root of the height in feet. So the dip correction also corrected for atmospheric refraction. Corrected for atmospheric refraction, the deviation on a flat Earth still came out at an average of 60.65%. The calculated distance to the horizon on a spherical Earth came out to be slightly more than 3/4 of the given distance, with an average deviation of 25.2%. After correcting for atmospheric refraction, the deviation was reduced to an average of 6.14%. The distance to the horizon was calculated along the line of sight. To be sure, I also calculated the distance along the surface using the 60 nautical miles per degree formula. The difference with the line of sight calculations varied from 0.054 to 0.071%. This is secondary evidence that the tables for dip correction were meant to be used on a spherical Earth. On a flat Earth they would be useless. But it also shows that the whole flat Earth argument that you see a horizon on a flat Earth in the first place because you only can see so far is bollocks. It would indicate that at an eye height of 1 foot you can only see as far as 1,000 meters. That is slightly more than 0.6 miles. Nobody in their right mind would ever believe that. Still, flat earthers do, and they do it on a daily basis.